Consider a mathematical transformation that guarantees open regions remain strictly open, even across infinite dimensional spaces. This structural preservation relies on the rigid interplay between completeness and linearity. This split-screen diagram highlights the difference between a continuous and an open mapping. On the left, a continuous function pulls an open dotted line boundary backward to space X. On the right, an open mapping pushes an open boundary forward into space Y. To see why this distinction matters, we can look at the standard sine function. It is a perfectly continuous mapping, but it is not an open mapping. Here is the open domain of 0 to 2 pi, represented by the dashed line segment on the horizontal axis. When passed through the sine wave curve, the output is the solid vertical line segment from -1 to 1 with closed brackets. While continuous functions can squash open boundaries into closed hard edges, open mappings strictly forbid this. They maintain the structural, open integrity of the space as they move it forward. The Open Mapping Theorem guarantees this behavior, but only under strict prerequisites. We need a linear operator that is both bounded and surjective, moving between two complete Banach spaces. This brings us to the core engine of the proof, lemma 4.12.3. This lemma states that if we map an open unit ball from the domain, its image in the target space will contain a smaller, perfect open ball centered exactly at the origin. We start step A by taking expanding spheres in space X, which map to these overlapping blobs in space Y. By applying the Baire-Tategori theorem, we prove that the closure of one of these mapped blobs, its hard solid outline, must contain an open sphere. In step B, we take advantage of the operator's linearity. We can take that glowing open sphere, slide it directly to the origin, and smoothly scale it to a precise defined radius. For step C, we must prove the actual image, not just its closure, contains our sphere. We construct an infinite sequence of narrowing vectors approaching a target point Y. The mathematical sum of this sequence converges to a precise point X back in the domain space, proving that point Y is fully reachable. Completing Baire's category theorem and calculating infinite Cauchy limits both require a space without microscopic gaps. A Banach space's completeness provides the mathematical floor that allows these limits to converge without falling through holes in the space. We now have a rule proven specifically for a unit ball at the origin. The next challenge is scaling this hyperspecific lemma up to prove the rule for any arbitrary open set mapped by our operator. Let's take an arbitrary open shape containing a point X. We can place a small circle around X, shift that circle to the origin, and then scale it down to a radius of 1. We apply our lemma to this normalized circle, which creates a mapped blob containing an inner ball at the origin. By reversing the math, scaling that inner ball back up, and sliding it along a vector, we create a perfect open boundary surrounding point Y within the mapped shape. Because linear operators perfectly preserve translation and scaling, the logic holds backward and forward. Proving openness for the origin's unit ball mathematically guarantees openness for the entire mapped space. This flowchart illustrates an immediate powerful consequence called the bounded inverse theorem. If our open mapping is also bijective, its inverse mapping will pull open sets back to open sets. Pulling open target sets back to open starting sets is the literal definition of continuity. And for linear operators, continuity equates directly to boundedness. This table compares the three foundational pillars of functional analysis: the Hahn-Banach theorem, the Uniform Boundedness Theorem, and the Open Mapping Theorem. Together, they establish the rules for extending functionals, bounding families of operators, and preserving topological structures. This specific corollary is heavily utilized in differential equations. Proving that an inverse operator is bounded ensures that solutions depend continuously on their given data, preventing microscopic input errors from causing massive output failures. Mathematical completeness is the engine that makes the proofs function. But the Open Mapping Theorem's ultimate utility is ensuring that structural boundaries are safely preserved when mapping forward into an infinite dimensional target space.